the 25,000 MPH Atmospheric Bounce. Orion's heat shield just endured 5,000 degrees Fahrenheit in a maneuver that saw the spacecraft literally bounce off the atmosphere at 25,000 miles per hour. This skip entry is not a comfort feature for the crew. It is a brutal stress test of the thermal protection system's recovery period. By dipping into the upper atmosphere and then skipping back out into a high-altitude arc, engineers are testing whether the shield can survive two distinct heating pulses. This maneuver is the specific delta that separates a standard lunar return from a viable Mars return strategy. Steering with an offset gravity center, the skip entry works because Orion is intentionally unbalanced. By shifting its center of gravity, the capsule generates a lift-to-drag ratio of about 0.3. To perform the skip, the flight computer rolls the capsule to point its lift vector toward the stars, pulling it out of the thick air before it can overheat. This mechanical steering allows the vehicle to target a landing site 6,000 miles away from its initial entry point. This precision effectively kills the recovery logistics nightmare of mid-Pacific search zones. However, this steering capability is secondary to the thermal soak problem occurring inside the shield material. The dangerous thermal soak phase. During the skip phase, the capsule exits the dense atmosphere for several minutes of relative cooling. This creates a thermal soak, where the extreme heat on the avcoat surface migrates inward toward the titanium substructure. Artemis 2 data indicates that the bond line temperature remained within a 12% margin of the engineering model. This is the critical constraint. If the heat penetrates too deeply during the skip, the shield's structural adhesive could fail before the second re-entry. We are no longer guessing at the char rate of the blocks. We now have crude mission data for dual-pulse heat loads. Scaling physics for the Mars return. Returning from Mars involves velocities exceeding 12 kilometers per second, which is nearly 20% faster than the Artemis 2 return. The skip entry validated this month proves that the heat shield can dissipate that extra kinetic energy by spreading the thermal load over a longer duration. Without this maneuver, a Mars-bound shield would require a 30% increase in mass to prevent burn-through. In the weight-sensitive world of interplanetary transit, that mass savings is the difference between carrying life support for 4 astronauts or just 2. This data point is the primary architectural bridge to the red planet, the signal under the noise. The success of the Artemis 2 skip entry moves the Mars return problem from a material science unknown to a standard ballistic calculation. By validating the thermal soak rates and char layer consistency of the avcoat block architecture, NASA has confirmed that our current thermal protection envelope can handle the 12 km per second velocities required for a direct interplanetary return. This effectively de-risks the most dangerous phase of a Mars mission. For engineers and mission strategists, the landing accuracy is a distraction. The real takeaway is that the bond line temperature margins held firm under dual-pulse heating. This proves that the shield's mass-to-protection ratio is optimized for deep space. The next specific indicator to watch is the post-flight ultrasonic inspection of the heat shield's internal structure. If the internal erosion matches the May 2026 telemetry data, the design for the Mars Transit Vehicle's recovery system is essentially finalized. Subscribe for more.